Today I'll talk about what's the state of art in machine learning, right? So first of all, it's deep. I think everybody here has come across deep learning. And I hope most of you were around for the earlier talk by Julian on MXNet and deep learning. So deep learning is really at the forefront of performance in machine learning. But also it's distributed, right? So again, MXNet that Julian introduced is very efficient across multiple machines, both lots of GPUs, maybe lots of CPUs. The idea is nowadays we have lots of data as well as models that are growing bigger, so you do want distributed computation. That's at the core of modern machine learning. And the last part that's close to my research is about multiple dimensions. I think that's still like kind of coming up only recently on how we can exploit many different dimensions in the data, right? As well as design new neural network architectures that exploit these different dimensions. So indeed, deep learning has now yielded state-of-the-art performance in almost every domain you can think of. So it all started with image understanding. The famous ImageNet competition was where you had to recognize objects in images with high accuracy. And for the first time, the deep learning system beat classical styles of machine learning. And that's when the excitement of deep learning began. And so you can see the trend after that really picking up for deep learning. And since then, there has been exciting developments in almost every domain. When it comes to speech recognition, speech synthesis, natural language processing, and most recently, autonomous driving. Right? So each domain has its own challenges, but the beauty of deep learning is it's domain agnostic, right? So it's applicable broadly to any domain. It does not need to know the details of the domain, but at the same time, for different domains, how the performance is, and can you design architectures that exploit the inductive bias present in different kinds of data is where it gets very interesting. So that's about deep learning, right? So at the core of it, what deep learning means is you have multiple layers of processing. So that's why it's called deep as opposed to shallow, right? So classical networks, those that were around in the 80s or even earlier, used very few layers, maybe even just one layer of processing, and that just didn't work very well. And that's where the modern networks differ in having now multiple layers, even as much as hundreds of layers of computation. And the idea is this helps you combine simple features into more complex ones as you go through these layers of computation, and hence get very high levels of accuracy when you do classification at the end of it. Right? So that's the canonical setting where in the case of image classification, you input the image, you send it through these layers of processing, and at the end of it, you get an answer of what objects are present in the image. Right? So if you've done the training well in this example, you would get that the probability that there is a dog in this image is very high. Right? At the same time, you may end up with some lower confidence levels of other objects such as cat, because that's close to the dog, but maybe at the same time, the deep learning system can distinguish the two, and hence you would get these with different confidence levels. And so this is the most common example for deep learning. And some of the details involve on what kind of computation occurs in each layer. And this is where the domain being images, right, makes a difference. And the use of convolution enables us to extract features from images in a translation-independent way. Meaning, no matter where the dog is placed in the image, you're extracting the same features out of it. Right? That's what the convolution operation enables you to do. And at the same time, it's very efficient because you have very small filters that go through even arbitrarily large images, and hence you can process this very quickly. Yeah. So, indeed, this is great. I mean, this yields state-of-the-art performance. What I want to touch upon is how do we now implement this, right, very seamlessly and easily. We expect data scientists to be not expert programmers, right? So there is indeed a rare breed who are both. But the idea is data scientists are those who understand machine learning principles very well and may be able to program in languages such as Python, but may not understand very system-specific details of how to optimize at scale, how to distribute across multiple machines, and so on. And that's where we need robust and efficient software packages that enables all this in the back end without an average data scientist having to worry about it. And so that's the idea. Can we have quite complex networks be defined through very simple operations, so provide a flexible and an easy programming framework? Right, so the example I've shown here is the Inception v3 network. This is one of the state-of-the-art networks, so meaning it has some of the best performance on ImageNet benchmarks. As you can see, it's quite complex. Without worrying about what each layer is doing, you can see that there is, in fact, like about 100 layers of processing. So even sending a single image through this network requires more than 1 billion operations, right? I think that's mind-boggling to me. I mean, the precise reason why we couldn't do this in the earlier decades was this, right? We just didn't have that kind of processing capability, and that appears to be the key to get this very high performance. So now the question is, how do we do this very efficiently? And that's where GPUs come into play, right? So GPUs are much more efficient for parallelizing operations, and especially matrix operations that these deep networks rely on. And that's why they've become the processing platform of choice for deep learning. And so that's one about computation, being able to do lots of computation in parallel. The other is memory. As these models get also bigger, how do we manage memory, and how do we make code portable across a variety of platforms and applications, right? And those could have different memory requirements. So let us now see how MXNet provides a very good answer for all these features. Right, it's a flexible programming paradigm. MXNet stands for Mixed Network Programming. We'll see that you can do both declarative and imperative style of programming mixed in your framework, and hence get the best performance as well as ease of programmability through that. And we'll also see how it's portable across frameworks, and it's also highly efficient. It's the most efficient framework on a variety of benchmarks. There's sometimes I'll try to be closer. Right, so that's the idea. Indeed, there is a whole choice of frameworks today, and it started like all the way at Theano, right? Just a few days ago, it was announced that Theano will no longer be supported. So indeed, you see a maturation of packages and a very fast evolving environment where new packages are being introduced. And there is Caffe, then there is TensorFlow, and then there is MXNet. Today I'll also talk about Gluon, which is the latest layer on top of MXNet that really combines the best of all features that's present in packages up to date. And we'll see what are the really the benefits of Gluon over the existing ones. right? So the idea is in Gluon, what you can do is you can write very simple code and yet get very high performance. So how is this possible? So what's happening in the back end is you can convert your imperative style of program, right? So you can write in Python. So this is a simple set of code where what I'm doing is just initializing two matrices, multiplying, doing an addition. Right, so this is Python, but also MXNet has a whole range of choices. You can use any of these other languages to do your front-end programming. But what's happening in the back end is it's able to generate this symbolic code. So as you can see, like writing in a symbolic way is laborious, right? So you have to declare every variable. It makes for longer code. It's harder to read. So it's not really, somebody would want to do this, but usually they're forced to do it. But what MXNet gives you is the ability to automatically generate the symbolic code given the imperative code with the new Gluon framework. And this is called the hybridization process. And once you have the computation graph, it's portable, so you can run it across a range of platforms. And that's the latest feature that makes it very flexible. So in addition to doing that, there is a lot of optimization happening in the back end. You'll see there is auto-parallelization. There's operator fusion to really exploit the best level of parallelism. Right, and there's also memory optimization. So to do all this, you really need this computation graph, right? So that's what this generation of the symbolic computation graph gives you the ability to do all these operations, all these optimizations. And but as a programmer in the front end, you don't have to worry about it. You can write very simple code. And that's what the Gluon framework gives you the ability to do. Yeah, so that's kind of the idea that symbolic is great if you want the code to be highly optimal as well as portable, because once you have the symbolic graph, you can port it across platforms. But the imperative is the flexible one. It's easy to do. It's something that even a novice programmer can write, but just by itself, it's not efficient, right? And what Gluon does is it matches the two. It gives you the best of both the worlds. So you write it in imperative style, and you get the performance that comes out of declarative style or symbolic style. So let me talk a little bit about how MXNet parallelizes across multiple GPUs, could be also across multiple machines. So this example here shows the computation graph with one CPU and two GPUs, right? So there is a simple forward pass and a backward pass happening in this data parallel mode, meaning each GPU has its own set of data that has been given to it, and it's doing this forward and backward pass. And as it does the backward pass, the gradients are being aggregated back in the CPU. Right, so again, you can see just even in this very simple framework, there are just so many communications and computations. Right, so the classical style of parallel programming was MPI, where you went into every low-level detail, you specified what needed to be stored where, when you communicated, and so on. And that's just not feasible with these modern systems. And so that's where MXNet in the back end will take care of it for you, and it does it in a modular way. So you get good performance without having to worry about writing parallel code. Right? So at the outset, it does some simple things, right? So this is pretty straightforward. What you want to do is, given the computation graph, you want to auto-parallelize. So if you see like two branches in the graph, you know that these two can be executed in parallel, right? And so that's what it does. Like it's able to parse the computation graph and make these decisions on when to parallelize. And as I mentioned, the simplest form of parallelism is data parallelism, meaning each computation unit, in this case GPU, has its own set of data on which it processes. The much more complex one is the model parallelism, and again, it depends on the setting. In at least most of the standard cases, we can get away without doing model parallelism if the models are small enough, if they can fit in memory in each GPU. But if not, we'd have to do that as well. Right? So the idea behind data parallelism, as I said, is each GPU has its own data. So what it does is this parameter server idea, where from the server it pulls the parameters. So it asks what are the current estimate of the parameters. So it's just all the same across all the GPUs. And then it does the own update. Right? So with this new batch of data, you're updating the gradient locally in each GPU. And then you push out these updates of the gradient back to the server. And the server aggregates the gradient and pulls, and you can again pull out of it again. So it's a very simple push-pull operation, right? So this is kind of as simple as it gets. But really the strength of MXNet is how to make all these operations lightweight and give you very high efficiency. So meaning if you go now from 1 GPU to 2 GPUs to 4 GPUs and so on, right? If you're doubling the number of GPUs, you expect your throughput to double, right? That's the ideal case. And we want to get as close as possible to the ideal case by trying to avoid different kinds of overhead, by trying to make the communication lightweight. And that's what MXNet is optimized to do. Right, so in this, it's easy to see that you can extend the same framework also to multiple machines. So there you would be doing the parameter server across the network, so you'd be sharing the gradients across the network as opposed to the GPUs within the same machine. So it's the same principle, but you do expect to incur more overhead because now you're running this over the network. And again, depending on the scale of data, depending on what you want to process, you may be forced to go to multiple machines. All right, so how MXNet makes it efficient is through this notion of a hierarchical parameter server. So we know that there is different levels of hierarchy when it comes to the bandwidth. Right, the slowest is pulling data from the network. And then going from CPU to GPU, right, is the next one. But inter-GPU communication is very fast. And this is where you want to use one of the GPUs itself as a level 1 server. So meaning all the aggregation of gradients from different GPUs happens at one of the GPUs. Right? So this exploits the fact that this is very fast. And then you only send the aggregated data to your CPU. And so this ensures that you reduce your communication overhead. And so in this experiment, we'll see that with the ImageNet benchmark and using the P216X large instance, so that is 16 GPUs, what kind of efficiency we'll get. So there are many plots here, but the first thing to note is, how much time is it taking per batch? So sorry about the typo there. So we are having a batch of images, and so this is inference, right? We are pushing that through the network, and we are asking how fast can I do it? And indeed, as you're increasing the batch size, so you're going from 2 to now 16, you do expect your time to increase, right? So going this way upwards is natural. But what I want you to pay attention is how the curve is within the same batch size, right? Because you're keeping the batch size per GPU the same, and then you're adding more and more GPUs. So in the ideal case, this line should be just horizontal. Right, because no matter how many GPUs you add, the time it takes to process each batch should be the same, right? Because now in each GPU, it just goes about doing the processing, you get virtually the same number, right? But that, of course, there is some overhead. So you do have the time increasing slightly, but not by much. And as you can see, if you can process in the large batch setting, meaning you take a large batch of data and do the processing, your communication ratio of your communication cost goes down. And that's why you can get very high efficiency here. And so the overhead that you incur is also a function of your batch. But you can see MXNet is efficient in this large batch setting. So next is the training. Oops. Sorry, I don't know why this is not. Let me. I should have turned off the wireless. Yeah, so you can also now ask, can I train across different batch sizes? And that's where it's challenging. So one of the open problems is how do you train on larger batch sizes? As you see here, it gets less stable as you increase the batch size. So this is one of the open problems right now this prevents us from scaling indefinitely, right? Because like kind of in the ideal world, you just keep adding more and more GPUs, and you will incur some amount of communication cost, but if you keep the batch size large, that cost is quite small, relatively. But training with large batches is a challenge, and this is something where a lot of research is being done to see how we can overcome that. But it's an exciting one. But really, there's a lot of progress that's been made, right? So I think the first ImageNet contest that was won by the Deep Network took months, maybe 7-8 months or something to train. And now we've gotten up to the state of the art is about half a day or even quicker, depending on the type of instance you learn. So if with 160 GPUs, you can get it down to half a day. And that's the idea that this now is fast coming down. You really want to look forward to the next set of things where you can train very large models very quickly. Right? And that's where AWS is breaking down these barriers, because it's making it possible for anybody to access this large amount of compute infrastructure and be able to train large-scale models. So before I get to the next part about learning in multiple dimensions, let me show you briefly these Jupyter notebooks with the Gluon interface. So I won't have the time to run them in detail, but I want to point you to the website. So this is the Gluon under MXNet. And one of my scientists, Zach Lipton, has put in a lot of time to make these tutorials. And there are also many other contributors. So this is a team effort. You can see that it starts from really fundamentals. So even if you have no machine learning background, this is a great place to start, because you can get the very understanding. There are notebooks that allow you to design simple things like linear regression, but from scratch, right? So you're not just in a black box way writing these functions. You can also learn how to code from scratch if you want to learn the principles. But at the same time, if you want something working very quickly, this templates really help you get started as well. And so I'll just very quickly show you this, when it comes to performance and what's special about Gluon. Because I think Julian showed some of the notebooks specific to different kinds of networks. So I'll show you briefly about this notion of hybridization, which converts imperative code to the symbolic code and helps you optimize your programs. Right. So the idea is you write this using a hybrid sequential. So earlier, the sequential was the notion to stack layers, but with hybrid sequential, you're giving the command that you will hybridize, or rather convert this from imperative to symbolic code. So as before, it's like constructing a multi-layer perceptron is very simple, right? You kind of add these dense layers or fully connected layers with ReLU. And yeah, so what you've done right now is write this imperative code. So writing this in Python. So this is still just imperative code, right? So if you just run it as it is, this is still in the imperative format. But now when you call hybridize, that's when you can obtain the symbolic graph. So you can, all you have to do is just say net.hybridize. And when you see the performance, like there is a performance improvement after hybridization. Naturally, since now in the backend you're doing operator fusion, you're doing all this auto parallelization and so on. So you'll get better for performance after hybridization. And you can now also access the symbolic program. So what it's shown here is with the JSON definition, you can see precisely like what the operations are, what the types are, everything, right? So you can now get access to this symbolic code and then run it across different platforms. So I won't give more details, but this is the idea. And also there is code to train on multiple GPUs very quickly and very easily. So it's essentially exactly the same as single machine code, but you're just kind of distributing it across GPUs or across multiple machines. So I encourage you to go with this tutorial, run these Jupyter notebooks. You can either locally install them or run on AWS. By the way, this is not available in the Army because it's still very new, but you can always just pip install and run this. Great, so now let me get to the second part of the talk on where do we go next, right? So deep learning, it sounds like, from what I told you, has solved all the world's problems, and we have to worry about our AI overlords. Not true, so don't quote me on that. So, indeed, there are lots of challenges to resolve. I think we're barely scratching the surface here. And, even before we head to the question of what's true intelligence, right, even to be just thinking about these specific tasks and getting the best possible performance, we are hardly there. Right, so this example of image classification task that I told you, I told that the numbers are really great, but that's with a lot of caveats, right? So humans, like infants, can recognize images very quickly and with very few examples, right? And there's a lot of unsupervised learning that's happening in our brains. So how do the machines do that, right? We don't have answers there. Right? And how do we think about combining different modalities? So, infants learn both with pictures and sound and with movement, right? All these aspects that the machines still don't know how to fuse different modalities. And that's where, in this part, we will see how we can extend now notions of matrices to higher dimensions to naturally encode now different modalities or higher order relationships in data. So indeed, I think everyone's familiar with the idea of scalars, vectors, and matrices, right? So in your linear algebra class, scalar is a single number, vector, right, is one-dimensional, your matrix is two-dimensional. Now, what are tensors? Tensors now are, in fact, these are special cases of the tensor, and tensors can be in any arbitrary dimension. And indeed, the data, if you think about it, is inherently multidimensional, right? So even if the data itself is a vector, or in the case of an image, a matrix, if you think about the relationships between different pixels or different coordinates, right, you can keep going to higher order relationships. That is, you can look at the mean, which is just the first order moment. You can look at pairwise correlations, that's the second order moment. You can look at now correlation among triplets, that's third order. So this is what I mean by data being inherently multidimensional, because you can write down the relationships in arbitrary dimensions, right? And so how do we incorporate all this very efficiently? And that's where I argue that tensors are important. In fact, tensors should be really at the core of thinking of a deep learning system. Right? Because if you think about it, what is deep learning doing? It is doing processing in multiple layers. So if you now input a tensor, so in the case of images, you have width, height, and number of channels. Right? Typically, if it's an RGB image, it's 3 channels. But then it's going through these different layers, right? In the convolutional layers, you're now changing the dimensions of your image, and at the same time, you're increasing the number of channels because you did processing through lots of different filters. So in essence, what's going on is you can abstract each layer processing as processing tensors, right? So you're having an input as a tensor, and you have an output. In the case of images, it could be a vector which gives you the confidence levels, but in the most general case, it could also be a tensor, right? So it's a tensor input, tensor output system, right? And now we can go from first principles and ask, how do I do processing in each layer that also involves tensor computations? I mean, we use matrices to do our computation because that's what we are most familiar with. And we also have very efficient packages, right? BLAS has these different levels of computation, and it's been highly optimized. But my argument is for the next set of things, we want to go beyond that and think about doing operations on tensors. So what does it mean to do operations on tensors? Right, so with matrices, what we know to do best, right, the most basic primitive is multiplication. So I can multiply the matrix on either direction, right? I can either multiply on the left or the right. So now with tensors, I have a lot more flexibility. I have, in this case, a third order tensor. I can now multiply in 3 different directions. Right, so these are generally called contractions because you could be reducing the size of your tensor through these operations. And so that's one of the first things we realized, that you can now incorporate these tensor contractions into your deep learning architecture. So this is the classical AlexNet. That's one of the first deep learning systems, right, that won the ImageNet contest. And as you can see here, it's taking the image, it's doing these computations in the convolution layer that is changing both the width and its height, but also the number of channels, right? But what's happening in the end is it's taking these tensor and flattening it into a vector. And in these fully connected or dense layers, you're doing a matrix multiplication. So you're multiplying this vector with a matrix. You're then doing ReLU or some nonlinearity, and at the very end, you have a softmax layer. Right? So that's the standard architecture. So the first question we can ask is, why should I do this here? Right? I'm destroying information by converting my tensor, my 3-dimensional object, into a vector which is 1-dimensional. So what if I retained this tensor as it is, but did these kind of contractions? So it's a very simple first step, right? And what benefit do we get by doing this? So intuitively, we are providing more information in our architecture, right, about these different dimensions. And that's what the tensors allow you to do. So this is the symbolic graph. Don't worry about it. All it's doing is this simple multiplication along these different directions. So what we found is if you use the tensor contraction layer in place of the fully connected layer, but kept the last layer the same, so it's still softmax, on these VGG and AlexNet, you get a huge amount of space savings. So meaning you have these networks with significantly smaller number of parameters and yet almost giving the same performance. These fully connected layers in these networks are very expensive, right? They make up a large proportion of the parameters. And with this methodology, you can significantly reduce that. So the other aspect is also now computing with tensors in the last layers. So doing now regression, you can even exploit the tensor structure in your weight matrix. So now it's a weight tensor, and you make this to be also having a notion of low rank in the tensor space. And with this, like without worrying about the details, you can also get significant performance boost. So this is like the amount of space saving. As you can see, even if you go to like more than 70% of your original parameter count, you almost retain the accuracy. So this is saying that if you exploit the tensor structure in your activations, right, like you went through the convolution layers, you got this activation tensor, you're retaining this as a tensor and doing tensor computations, you can significantly reduce the size of your network without affecting accuracy. And indeed, the smaller the network is, it is faster, it will consume less memory, you can run it on smaller devices, right? So lots of benefit that come out of having more compact networks. And this is one application where tensor can play a role. Right, and now we are investigating all kinds of other models with sequence models, right? The recurrent neural networks. There are very interesting things you can do with the use of tensors and do much better long-term prediction as opposed to the standard recurrent neural networks. So I think there are many interesting cases of using tensors into your neural network architectures. So you can also use tensors when you want to combine different modalities. One example is visual question and answering. So in visual question and answering, what you're given is an input image, a question, you want to generate an answer. Right? So you do expect the question to be about the image, otherwise it's kind of the two are not related. So because now both the image and this question text are related to one another, you want to like pool these different modalities together. And you want to do it without rather blowing up the dimension. Right? So by pooling, I mean you can look at the cross moment between your image features and your text features. But just like the cross moment means it's the multiplication of dimensions, and that's huge. Right? And if you want higher order moments, it's even bigger. So you don't want to explicitly write down these moments. You want to compute this implicitly, and that's where this notion of tensor sketches helps you. So I'm not going into the details of the math, but really kind of just to roughly show you what it's doing simple operations like fast Fourier transform, some count sketches, right? That's a simple notion of hashing, and be still able to get like approximate higher order moments that look at cross correlations between your image and text. So another interesting aspect that you can do with tensors is decompositions. With matrices, we're all aware of singular value decomposition, right? You can take your matrix, you can do low rank approximations. Now you can extend this to higher dimensions, and it gets very interesting. There are different notions of rank that comes with tensors, and different operations gives you different properties. So you can now exploit this to extract hidden factors in your data in an unsupervised way. So as I mentioned, when in these standard applications that I showed you, the images come with labels. Right? So if your data doesn't have labels, it's challenging, and that's where these techniques will help you do unsupervised learning in an efficient way. I'll give you a simple example of how this is possible, why tensor decompositions are better than matrix decomposition. So this goes back to a classical problem that Spearman was worried about way back in 1900s. Right, so he wanted to like decompose intelligence in people, right? So he wanted like what are the different factors of different kinds of intelligence. So he grouped it as there's a notion of verbal intelligence and mathematical intelligence. So can I decouple the two by testing people on different kinds of tests? right? So you can imagine maybe each test is kind of a combination of these different skill sets. So you want to like just let the data speak for itself, and you want to see the structure of both verbal and mathematical intelligence showing up in these tests. And one of the simplest things you can do is you can take the matrix of students and the tests, right, the scores of students in various tests, and decompose that through your singular value decomposition. But it turns out that this is not unique, right? So you can do different decompositions and you can still get the same matrix. And it's only unique if you assume that the factor of verbal and mathematical intelligence are orthogonal to one another. And this is not realistic because you expect these intelligence factors to be quite related to one another. And so that's the limitation of matrix decomposition. And well, there's music when there are tensors. So now how do I think of tensors, right? So as I said, tensors allows you to introduce more dimensionality. So now you can think of it as not having a single matrix, but two matrices or multiple matrices. So I'm doing two different series of tests on the same subjects, on the same students, but maybe one is oral, one is written, right? And I want to assume that the factors of intelligence are shared across these different types of tests. And so if I assume this, I can essentially combine these different matrices and express this as a tensor decomposition. So all I've done now is just assemble the two matrices into a cube, right? But what's really the new notion here is incorporating the constraints that the same factors of verbal intelligence are present both across oral tests and written tests. And so that enables me to combine these constraints as a low-rank tensor. And a low-rank tensor is much more powerful than a low-rank matrix. And so what this means is essentially once you have a tensor decomposition, you get uniqueness under much weaker conditions compared to the matrix. Right? So this again has very rich theory. It goes back to the Kruskal, who is also looking at spanning tree algorithms, if you recall your algorithms course. Right? So there's a lot of rich history behind tensors, but to me the interesting aspect is once you have a tensor and you want to ask when is the decomposition unique, the conditions are much weaker than when it comes to a matrix. Right? Without going into the details, the intuition is what it says is a tensor has more information. In the example that I showed, instead of one set of tests, you have now two sets of tests or multiple sets of tests. So you have more information, but you also have more constraints. So that means if there are really this hypothesis of underlying hidden factors of different kinds of intelligence, you can discover them under much weaker conditions. In this instance, all you need is them to be linearly independent, which is a very weak form of non-redundancy, right? So you don't want the two factors to have exactly the same vector representation. And that's a very mild condition. And so that's kind of the theory behind this, that tensors pack in a lot of rich information. And by imposing the relevant constraints, you can also exploit this multidimensional nature in a very strong way. So, okay, that's great theory. That's lovely math. In fact, tensors also first appeared in quantum physics and chemistry, right? But what about the relevance to machine learning? How do we do this? And so this is where you can apply it for unsupervised learning in text. So one of the popular applications is document categorization. So you give your machine a bunch of documents without telling what the documents are about. Can it automatically classify them? Right? So in this example here, it's a news article. So if I were to ask you what this document is about, you can't read the text, but you can read the title. you can already say, oh, this is about a university, right? Florida State. It's about football, so that's a kind of sports. And there is justice, so some kind of crime may be involved there. So humans are very natural in inferring this, right? So there isn't a single category. It's now these multiple different categories this document belongs to. And so you can't do your standard clustering because that would try to classify this to only one category. And so this is where this class of latent Dirichlet allocation models have been very popular. And we can use these tensor methods to learn such models at scale very efficiently. The basic idea is what you do is you're looking at now these higher order moments of your word frequencies. Right, so if I told you the article contained word apple significantly, right? So the word apple occurred a lot of times in the article. And if I asked you what the article is about, right, you're not sure. Maybe it's about the software company or, maybe it's about fruits, right? But if they both apple and banana occurred in the article a lot of times, you know that this is about fruits. Right? So now if apple, banana, and orange occurred a lot in the document, you're even more sure it's about fruits. So that's the intuition here. By looking at correlations between multiple words, how they occur in documents, you can naturally pick out these different topic categories. And you can do that by decomposing your co-occurrence tensor. So you look at the counts of how many triplets of words occur in a range of documents, and by decomposing that tensor, you can show that different topics naturally emerge out of this. So this is the idea that these tensors pack in structure of different hidden factors, in this case, different topics in documents, and this emerges when you decompose the tensor. And so there are lots of interesting algorithms that arise from that. I won't give the details, but compared to some of the earlier methods, these are much faster and more accurate in being able to extract these hidden factors. So before I conclude, I can again show you some notebooks and some packages for doing tensor computations. So Tensorly is a package, the primary contributor is Jean Kosafi. He interned with me, and since then we've had a number of very interesting capabilities with Tensorly. So you can go to the website, you can do very simple installation. And there are, again, some Jupyter notebooks that will help you understand tensors very easily. Right, so there is like the basics notebook. It shows you how to create different tensors. You can create them by taking matrix slices, right? Different matrices you take as slices and you can define the tensor. You can also create in other ways. And the nice thing here is now, originally it was written as a Python package with NumPy. But then Sean has added now MXNet backend as well as PyTorch backend. So the idea again is we want to give our customers or users flexibility in what they want to use. So now you can have the capability of multiple GPUs and multiple machines and still run tensor operations very efficiently. So there are operations like unfolding, which is converting tensor to a matrix. So all these things you can go through. So what I want to show you now is the tensor regression networks that I described as being able to get very high compression rates, meaning it has a huge amount of space savings in terms of number of parameters and still gives you high performance. So the full paper is available on arXiv. But I want to show you how simple it was to write the code in Gluon, right? So all it's done here is take the Tensorly and then set the MXNet backend, right? So it's doing that. So there's a lot of it that is very standard, as in the standard deep network for loading the data, right? So the only new part was writing this tensor regression layer. So you're writing this new last layer based on tensors, and without giving you all the details, all that was needed here is to, the core was the central part of your weight tensor, and the factors were the multipliers. So you just need to set them in that form, and that's it. It was just, and then you're just using your tensor regression layer in your network. So as you can see, all these other things are, and so when you're doing this, you do Tucker to tensor, because the Tucker was this form of representation of your weight matrix, and you can easily convert it into your weight tensor and start using it. So obviously I hid a lot of details, but it's really very few lines of code you need to write even these seemingly complex looking operations. So let me conclude by saying that MXNet has a number of attractive features. It gives you flexibility in programming. It has the best performance on multiple GPUs, on multiple machines. And now with the new Gluon framework, it's also very flexible in terms of allowing you to write in the imperative style, but giving you the ability to take your symbolic computation graphs and run it across a range of platforms. And in the last part, I showed how tensors, I think, are the future of deep learning because it exploits multiple dimensions in a natural way. And we want to think about new computation frameworks, new architectures that involve tensors. Thank you.
Thank you. Thank you. Thanks, Anima. Questions?
How does Gluon compare to Keras? Because the API looks really similar.
Yes. So Gluon is Keras and more, right? So the idea is Keras is great if you are doing those limited set of operations. But now with Gluon, you can also write new operators and get high performance. And by the way, with Keras, you can also use the MXNet backend. So Gluon is really if you also want to define new operators that are not currently present in Keras, right? You can do that and still get high efficiency. So that's the idea. The inspiration is from Keras, right? It's so simple to do, but it's limited in what you can do with it. And so Gluon adds to that.
Further?
Yeah.
Edita? Oh, sorry.
Well, I guess they're going there. So after that.
So,
well, you can get the emotion recognition on the recognition service. So it's already available.
As an API, by the way.
Yes. So, yeah, obviously there's always room to say when we can do better or how it does, right? But it's already available. I think. Yeah.
So what is the future hardware for deep learning? Do we continue to use GPUs, or there will be some new hardware specialized even for that? What's your opinion on that?
No, that's a great question. GPUs are great because they give you the ability to parallelize operations, right? But again, if you limit to these very specific set of operations, there is potential to be even better, and that's where there are so many now startups doing ASICs, right? There is a lot of interesting developments in the space. FPGAs again are you can always do things better with them, but the question is how much effort that'll go into the development and how much better can you do over GPUs, right? I think that's still open.
Right. I have one question.
Oh.
So maybe stand up. So you show that it's quite easily to parallelize your work on GPUs. So is it kind of done by automatically? So do you have any kind of control over how it's done?
So you can always go to the back end and do more optimizations or do this, right? So if you're an expert, you can always go to that layer.
But let's assume I'm not. So I have 2 GPUs installed on my computer. So I'd like my model to run on as much as horsepower I have on my computer.
Okay, and that's done automatically. So it depends what change you want to make on top of that.
Right. So but is it done by just batch size? Kind of each individual batch is distributed among different GPUs, or some more fine more granular operations are distributed?
So it's as simple as you just need to give like what your GPU context is. So if it's not multiple machines, just single machine, it's actually, it's like, I mean, it's just 2 lines. That's why I just want to show you here. So it's as simple as just defining what your different contexts are, and just that's it. Yeah.
Cool. Thank you very much. Thank you, Anima.
Thank you.